video, we're taking a look at magnetic materials and magnetization. So in this one, we're going to take a look at specifically electromagnets. So using a current to turn a metal into a magnet, essentially. So the first thing with electromagnets is we're not actually magnetizing the metal itself. What we're doing is we're essentially moving charged particles, which themselves then have a magnetic field. And the reason we use metals is because they have electrons which are free to move around. Okay, so first of all, let's look at why a current carrying wire has a magnetic field, because the wire by itself doesn't have a magnetic field. So let's step back a second and look at charged particles themselves. So what I'm showing over here in the left and on the middle are charged particles that are going into the page. So imagine them starting at your face, heading towards your computer or phone screen, whatever you're using. That's the direction the charged particles are moving. So if there's a positive charged particle moving in that direction, we get this clockwise field around it in this circular path. If it's negatively charged, we get this anti-clockwise field like this. If we change the direction it's moving, so now it's starting in the screen and coming out towards your face, you can see that the field is now in the opposite direction. So this is the key idea. So magnetic fields are formed around moving charged particles, and you can change the direction of that field by either altering the charge of the particle or by changing the direction the particle is moving. So in the middle, we've got the opposite field direction because we've got the opposite charge. On the right hand side, we've got the opposite field because we've got it traveling in the opposite direction. And this idea in particular on the right hand side is going to be important with electromagnets, because later on, if we reverse the current, we change the direction the charged particles are moving, so we change the field. Okay. So that's why we have a magnetic field. We've got moving charged particles. So how do we work out the direction of the field? Because I was showing you in that diagram, sometimes the field was clockwise, sometimes it was anti-clockwise. How do we know which it is? Well, Maxwell has come up with a rule that we can use to help us work out which way it's going, or at least remember which way it's going. So it's called the Maxwell's right-hand grip rule. So essentially, you take your right hand, and it is important it's your right hand, not your left hand, and you point your thumb in the direction of conventional current. And then your fingers will tell you whether the field is going clockwise or anti-clockwise. So you can see in the diagram, you can see there the thumb points upwards. So the fingers you can see are showing the direction of the field line arrows. So if we go back to the diagram we just had, so remember, conventional current is the direction that positive charges are going. Okay, so if we have a positive charge going into the page, I'm pointing at the screen with my thumb, and you can see my fingers are showing the field going clockwise. If we had a negative charge, that would mean we'd have it going in the opposite direction. If we had the positive charge coming out of the page, you can see your fingers now point in the opposite direction. If we're dealing with an electric circuit, we can identify the direction of conventional current by essentially identifying where positive charges would go. So positive charges come out of the big side and into the little side because they're repelled by the positive charge and they're attracted to the negative. So if you have a circuit, you can always work out which way conventional current is going. And from that, you can then work out your field direction and stuff like that. But that's what this is the rule we use, the Maxwell's right-hand grip rule. Okay, so what does this actually look like for real? So what you've got here is some iron filings around a current carrying wire. So from this diagram, we can't see field direction, but we can see where the field lines are. We can see we formed these concentric circles around the wire when there is a current in the wire. There's another kind of electromagnet we produce using a solenoid. So this is a wire which we've then wrapped up into coils, and it produces a field like you can see here. So on the diagram, the eye is showing you direction that conventional current is going, and that's going to be important in a second for working out why that's a south pole and why that's a north pole. So Inside the field, we get what we call a uniform field, so a region with constant field strength, because you can see the field lines are equally spaced. Whereas out here, we can see the field is getting weaker. Now, technically speaking, this diagram shouldn't be showing the field lines being cut off here, because the field lines always form a complete loop. So they should be going all the way around to the South Pole, but that would take up too much space on the page, which is why it's not been shown here. So the question is then, how do we work out which is the South Pole and which is the North Pole on this? So they've been labelled on the diagram, but how did we know that? So what we have to do is first imagine we're looking from the end of the coil. So to start with, we'll imagine we're looking from, say, the left-hand end. So if you look from the left-hand end, you would see the conventional current going in an anti-clockwise direction. So this black line is showing you the direction of current. It's not showing you field lines anymore. So if we looked at it from the left-hand end, we would see the current going round in a clockwise direction here, like you see on the diagram. And that's why it's a South Pole. So if you see current going clockwise, you are at the South Pole end. Likewise, if we looked from the right-hand end, we would see the current going in an anti-clockwise direction, which means that's what tells us we're at the North Pole end. And there's a handy way of remembering that. So if you actually draw the letters N and S, they need to be capitals, and you add arrows to the end of the letter, you can see that it actually indicates if we see current going anti-clockwise, it's north, or current going clockwise, it's south. So it's a handy way of remembering that. But that's how we know it's a north or a south pole. What do those actually look like with iron filings? Well, it looks a little bit like this. So you can see in the middle, we've got a fairly uniform field. So the field lines are fairly straight and fairly equally spaced. It's only close to where the current is going in and out of the page, we start getting these circles here. And on a larger scale, we can produce a longer one. And again, you see we get a fairly uniform field all the way through. It's only around the ends we see it starting to curve there. So if we remember in the previous video, we were looking at turning a material into a magnet using a current carrying wire with DC current. So if I stuck a material in here, so let's say I just put a block of steel in here, the domains in that material would all become aligned with this field, so they'd all become lined up like this. And we then turn it into a magnet. So that's how that actually works. Okay, so have a look at how we indicate the strength of our electromagnets. So on the left, you can see an example of a weak field, and on the right, you can see an example of a strong field. So you can see that on a strong field, the distance between field lines is shown as being much smaller. So the field lines are much closer together. And if we actually want to know where these field lines are, we can scatter iron filings around them. But that's how we show a weak and a strong field. The other thing I wanted to indicate using these diagrams is what the X and the dot mean. So the black bit in the middle is showing a wire that's going into the page. So if you see an X, that's in this case indicating that current is going into the page. Now sometimes X's are used for field lines as well. So X's generally speaking mean going into the page. In this context, we've got a conventional current going into the page through a wire. On the right hand side, the dot shows something coming out of the page. So in this context, it means conventional current coming out of the page. So we've looked at how we can use iron filings to show where the field lines are. How do we know what direction they are so that we were able to develop, say, the right-hand corkscrew rule or the north and south pole rules that we've seen earlier? So that's what we'd use a plotting compass for. So a plotting compass essentially has a needle with a tiny magnet on it, and that points in the direction of the field. So by moving a plotting compass around or using lots of plotting compasses, we can determine the direction of a field line at a given point, as the north pole of the compass will point in that direction. So this is how we've been able to put arrows on our diagrams. We found this out using a plotting compass. We do this for real. So here's a bar magnet, and here's a lot of plotting compasses arranged around it, and you can see that the arrows are all pointing in different directions. So the arrows just indicate the direction of the field. So we can see that we've actually put the compasses on a variety of different field lines here, but the arrows indicate the direction of the field line at that point. So this is a handy way of actually drawing these fields to represent something real. Okay, so we've talked about what a stronger field for an electromagnet looks like, but how do we actually achieve it? So if we just have a current carrying wire, you make its field strength, or you increase its field strength by increasing the current, or the potential difference across it. And so essentially, if we have just a wire, that's the only way we can go about increasing how strong it is. If we've coiled up that wire into a solenoid, we have two more options. We can increase the number of coils or turns inside the same length, and I'll show you what that means with a diagram in a second. Or what you can do is place a soft magnetic material, such as iron, inside the solenoid, because the iron's domains are going to align with the electromagnetic field, and that increases the overall strength of the field. So those are our three options for giving you a stronger electromagnet. And I want to develop the second option a little bit more to show you what that means. So here we've got two coils or two solenoids, and their coil length is the same for both. So that's what I've shown on the diagram there. But the right-hand one has more coils in the same length. So this would be a stronger electromagnet if they had the same current going through them. So how do we change the direction of a magnetic field? Well, earlier we saw that for a charged particle, we can change the direction of the field either by changing the charge, which isn't an option in a circuit because it's always electrons that are moving around, or we can change the direction that the charge is moving. So that's what we can do. So if we want to change the direction of an electromagnetic field, we would need to reverse the current. So essentially, we just change the connection to apply the potential difference in the other direction. Okay, so that's essentially what we saw earlier. So if we have our wire going into the page like we saw earlier, if we now have the current coming out of the page, we can see the field has reversed direction there. So that's our example we met earlier. Okay, so we're now going to start taking a look at things we use electromagnets for. So in the previous video, we met them being used to magnetize and demagnetize magnetic materials. Another device they get used in is called a relay. So it's essentially made up of three parts. We've got a solenoid, which will contain a DC current. So it is going to have its own magnetic field. We're going to put an iron core inside it just to make the field stronger. So that's what this line in it shows. It shows it's got an iron core in there. That makes this field stronger. And then we've got a metal switch over here, which is going to be open and closed by this electromagnet. So that's a relay. So what do we use relays? Well, the most common thing we use them for is for allowing a low power or low current circuit control a high power or high current circuit. So essentially what's happening is the current passing through the solenoid turns it into an electromagnet, and that electromagnet can then control the switch. So in terms of what this might look like, so here is our low power circuit. So we've just got a cell, maybe 1 volt in there with a coil. We're going to put a soft iron core inside that coil, and then that is going to be connected to another circuit with the switch in it. So this is our relay connecting one circuit to another. So we said we'd have a low power circuit. So on the left-hand side, this is our low power. So we've got a small potential difference. Our higher power might be a 12 volt. So this is an example of the ignition circuit in a car. Because what happens is your driver turns a key, which activates this low power, low current circuit. And that closes a switch, which activates this high power circuit. And the reason you do this is the user is then completely isolated from this high power circuit because they are not directly connected into it. There is a clear gap between the two. We're just using magnetic fields to bridge the gap in here. Okay, So the final thing we're going to take a look at with electromagnets is how they interact with other magnetic fields. And we get something called the catapult effect, and we'll see what that looks like. So we're going to look at the interaction between a current carrying wire and a permanent magnetic field. So we're going to create a permanent magnetic field using two bar magnets. So we're going to have a north pole on one side and a south pole on the other. Now, there is more that I've cut off this diagram. So there would be another south pole over on the left-hand side somewhere and another north pole over here on the right-hand side somewhere. But that's not important to what's going on, so which is why I haven't shown it. And we have the field lines going from north to south, and we've got a pretty uniform field in here. We're also going to have a current carrying wire where the current is going into the page, because I've shown it with an X. So the right-hand grip rule tells us the field is going clockwise around that. So my thumb points into the screen, and we can see the field goes clockwise. So this is what their two fields would look like separately. But what would they look like if we combine them together? Now, I'm going to show you a diagram that gives you the right idea in a second, and then I'm going to show you what it really looks like. So this diagram is useful because it helps us understand what is happening, but this is not what it actually looks like, because we've broken several of the key rules in that we've clearly got field lines crossing one another, which does not happen with magnetic fields. But it gives you the right idea, because essentially here at the top, we've got field lines in the same direction. The red ones are in the same direction as the black ones. So they are going to add together. At the bottom, the red ones are in the opposite directions to the black, so they are going to cancel out. So the resulting effect and what it actually looks like is this diagram here. So we get a lot of field lines pushed very close together on the top, and we get field lines which are spread out along the bottom. And this is why it's called the catapult effect, because you can imagine it's like you've stretched a catapult out and you've stored elastic potential energy. It's the same idea here, but what you get is a magnetic force, sometimes called a Lorentz force, that will act on the current carrying wire. So it will catapult the wire out of your permanent magnetic field. And the force goes from the region of high density to low density, or close to spread out here. So the F shows the force on the conductor. And this is because of the interaction between the two magnetic fields. And the force goes from the region of high field strength to the region of low field strength there. Now, there's something I haven't mentioned, is this magnetic field, the permanent one, would also experience a force. So if your conductor experiences a force from the permanent magnets will also experience a force from the conductor. But most diagrams will only show this one, the force on the conductor, because that's what they're trying to illustrate. But Newton's third law tells us there would also be this other force acting too. Okay,